Chastity Reed. Peter Postma of FilmLight gave an incredible presentation at the May 2009 LA Red Users Group gathering. His talk on color management was quite an eye-opener.
From scratch each time. Before that, I worked for about 5 years in Kodak, developing some color management and digital cinema technology. So I've been dealing with color management in the industry for quite a few years. I'll try to keep this informal. Please ask questions if there's something you don't understand that I'm talking about, or if you have a specific, color management, color issue that you've had in production that you still have lingering questions about. So a lot of people think color management is just getting the right LUT. There's this magical LUT fairy that will come and grant you the right lookup tables, and then once you have the right lookup table, everything's going to be fine. The problem is that a lookup table is a set of assumptions. It assumes how your monitor's set up, it assumes how your camera's set up, it assumes what kind of film out you're doing or other display device you're going to. So a lookup table may work very well in one scenario, and as soon as you change any of those variables, as soon as you change the display or change the camera or change something else, it doesn't work anymore. So you can't just trust that once a LUT has worked for you once, it's always going to work. You have to know that the right assumptions were put into that LUT, that the right color science essentially is behind it. So what are we talking about when we're talking about color? Color is the human perception of electromagnetic radiation, for lack of a less technical term. There's basically a narrow bandwidth that we see as everything from purple to red and everything in between, and that's our perception of color. So if there's more of those red wavelengths coming at us, we see an object as red. If there's more of those green wavelengths coming at us, we see an object as green. But typically, it will always be a spectrum of light. Very rarely do we see just very narrow red wavelength only coming at us. It's usually a continuous spectrum like this. And depending on the color mix, we'll see an object as more red or more green or more blue or whatever. As you probably know, we have three color receptors in our eye. We could call them red, green, and blue. Color scientists like to call it long wavelength, medium wavelength, and short wavelength. But basically, these three color receptors cover this range and are responsible for our perception of light. And that's why a display device is able to reproduce colors that we see using three colors, because it's basically just throwing light at those three receptors in our eye. So there's color space called the XYZ color space, which was developed by the CIE, a bunch of French guys in the early 19th century. Because all humans see color more or less the same way. There's very, very tiny variation from one person's color receptors to another person's color receptors. So we can kind of standardize the way humans see light, come up with a standard set of functions for the way those three receptors in our eye see light, and therefore use those formulas to convert from one display device to another to make sure that they match. The XYZ color space gives us this diagram, the CIE diagram, which represents all the colors the human eye can see. If you really want to talk about the entire visual perception, it'd be a 3D diagram, because this doesn't show luminance, it's just showing color range. But yeah, so on the outside of this diagram are all the pure wavelengths, and then depending on how those wavelengths are mixed together, you get all the colors in between. One of the neat things about this diagram is that if you plot a triangle on it, if you plot the three colors that a display device uses, so if I plot the green of this LCD and the blue of this LCD and the red of this LCD, all the colors inside that triangle are all the colors that display device can reproduce. So everything inside this triangle is what it can reproduce. It can't reproduce any colors outside of that triangle. So if I plot another display device, which is a slightly different red, green, and blue primary, it'll give me a different triangle, and I can see where they overlap, see where I can make the colors match, and see where I'm going to run into trouble. One of the other interesting things this diagram tells us is that there's no perfect display device using three colors that will reproduce all the colors the human eye can see. No colors exist outside this diagram, and so there's no triangle you can fit in this shape that will cover the whole range of the shape. So if you really wanted to cover every single color the human eye can see, you'd need 6 primaries or 8 primaries or more. But it's not a big deal because, again, those extreme colors at the edge, the pure electromagnetic spectrum colors, very seldom exist in nature. You really only will see them in a lab. So by picking a triangle within this, we're not really giving up any colors we would see in daily life. And you can actually see why this is when you look again at the sensitivity of the 3 receptors in our eye. You can see you could get a pretty pure blue down here. You could get a pretty pure red without any green or blue down here, and that's the other corner of the diagram. But if I pick a green, I'm always going to be giving something up. And that's because when we see green, we're always seeing a little bit of red and a little bit of blue with it. There's nowhere on this green sensitivity graph that I'm not also picking up a little bit of red or picking up a little bit of blue. So it's actually, there's kind of a color mix that goes on in our eye, and that's why there's no ideal monitor with 3 colors that will reproduce everything. So color management used to be pretty easy, especially for television, because you had millions of people with all more or less the same TV out there, and you only had a couple people producing content. So it made much more sense to put your color management in the camera and just tune the camera to give you good-looking images on your monitor without any mess or any fuss, rather than putting a whole bunch of expensive technology into every consumer set out there. So everyone had CRTs. The cameras were all tuned to make a good-looking image on the CRTs, and everybody was happy until LCDs, projectors, plasmas, everything else came around. And oh, by the way, we still have this film thing that's going to hang around for a couple of years that we have to deal with too. So there's all these other different display devices and technologies out there that have different strengths and weaknesses, different ways of reproducing color. So we need a way to deal with all this, and that's what color management does, is give you transforms and lookup tables that can then deal with these different display technologies. So when comparing different display devices, there's a couple things we need to make sure we look at. The first is the color gamut, which I've already sort of talked about. That's the range of colors a monitor can reproduce. What does that triangle look like? What are the mix of colors that display device can reproduce? The second is the tone reproduction. How does it get from black to white? Is it spend more time in the shadows, or is there more detail in the highlights? What's the transition from black to white? And then also, what's the overall dynamic range or contrast? What's the difference between the darkest black I can make and the brightest white I can make? There's some other things we have to look at as well. Resolution, obviously, which is pretty easy to understand, and any artifacts that a display device might have. They may have inherent motion artifacts like lag or motion blur or things like that, or flare. And there's a certain amount with color management tools we can deal with those artifacts, but at a certain point, it's just the inherent limitations of the monitor we have to deal with. So much more important is to deal with the color gamut and the tone reproduction and the contrast. So it's actually pretty easy to characterize a display device. We just need to measure the 3 primaries. What is the spectral output? What are those? Where on the graph do those 3 colors that fit, red, green, and blue? And what's the tone scale? So just measure grayscale, measure red, green, and blue, and you know every single color that display device can create. 4 additive displays with no crosstalk, and by that I mean pretty much any digital display device: CRT, LCD, plasma, DLA, LCOS, any of them. But not film or printing to a piece of paper, because film has crosstalk. When you ask for just cyan dye, you sometimes get a little bit of yellow and magenta with it. And likewise on print, the inks can bleed together in kind of strange ways. So you need more complex tools to be able to profile film and paper prints. But for digital display devices, you just need to know what are the primaries and what's the tone scale, and you're good to go. So there's two types of devices we have for measuring display devices. First is a tricolor meter, which uses 3 color sensors that try to approximate the 3 color sensors in our eye to basically see light the same way our eye sees light. And they give very fast readings. They're very accurate even at low light levels, but they can be subject to false readings because there are no 3 filters that we can manufacture that exactly match the color receptors in our eye. So there's always a little bit of a correction that has to be done to make the filters match our eye, and the amount you need to correct depends on what you're measuring. So you can make a tricolor meter that gives you totally accurate numbers for a CRT, but then you try to measure an LCD and it doesn't quite work right. Or you make it work for an LCD with a fluorescent backlight, but then you get an LCD with an LED backlight, and again, it doesn't quite work right. So tricolor meters are great, but you have to make sure you're using one that's tuned for the display device that you're measuring. Otherwise, you could be getting bad numbers.
The LA Red Users Group meets monthly at Kappa Studios in Burbank. From Hollywood, I'm Chastity Reed.